Picking back up where we left off on this example, you can see we actually had worked ahead. We wanted to find the midpoint in each of these subrectangles. Now it's important to note that in this first subinterval between 0 and 1, right between there is 0.5, so x would be 0.5. Likewise, between what we have for our y values of 1 and 1.5, directly in between there is 1.25. So this point in the middle would be 0.5, comma 1.25. Right between 1.5 and 2 would be 1.75. So the point dead center right in the middle, which would actually be the midpoint of that subrectangle, would have coordinates of 0.5, comma 1.75. Likewise, very similarly, between 1 and 2 would be an x value of 1.5. So the midpoints would be 1.5, comma 1.25 in this bottom right subrectangle, and the top right subrectangle we'd have 1.5 and 1.75. Now the area of each of these subrectangles, you can see that the x length would be 1, that's your delta x. Your delta y would be a half, and you can see that it'd be 1 times 1/2, which is 1/2. So the area of each base of that prism is 0.5. What we could do is definitely then multiply 0.5 to each of these heights corresponding to the midpoints. But in class we talked about factoring out that 0.5, since 0.5 would be constant for all of them. It's important to note that inside this double integral, our function is x minus 3y squared. So what we did is we just plugged in the corresponding x and y values, and then very quickly worked out those 4 distinct values. This is where it just turns into some number crunching, and it's just going to take a little bit of time and a little bit of patience to actually substitute in the corresponding x and y values. But rest assured, it won't take all that long in the end. With the 0.5 factored out in front, you'll just add all of these numbers together and multiply 0.5 times negative 23.75. You should get a final approximation for this integral to be negative 11.875. Notice once again, just as we saw in the past, last year in Calc BC, we saw that our integrals very well could have negative values. Our double integrals can have negative values as well. Our curve could dip below z equals 0. We deal with signed volume, so an integral would actually be net volume. Okay, to get into our very last example, let's remember that from last year we had the average value of a function, and we had to use that definition repeatedly. It was the integral from a to b of f of x dx multiplied to 1 over b minus a. Kind of what you might remember us doing is we went from a to b, and we could use the integral to get an estimate for that net area. And then we were dividing by this length of b minus a, or multiplying by 1 over it. Now, of course, in this context, you can see that our subinterval is two-dimensional. As we went back to R in the very, very beginning of this problem, R right here was a large rectangular region. Rather than having a length, we could talk about that having an area. And, that's more or less what this A of R is right here. So notice the double integral right here, sub R, it means integrate over that region R. Notice our differential is actually written as a dA. But as we do this, this is how we get an average value for a function in multivariable calculus. So here we have a contour map below. It's shown for a function. We need to change this to 0, 2 and 0, 2. And we want to use a midpoint rule with m equals n equals 2 to estimate the average value. First of all, if we look at this large R, we can see that we're going between 0 and 2 and 0 and 2. I hope you can quickly agree that the area of R is going to be 2 times 2, which is going to be a 4. So we'd write that as A parentheses R is equal to 4. But of course, in this picture off to the right, they have really allowed us to break this into subintervals of 2 for each of those lengths. And you can see as we're working this out, we're going from 0 to 1, 1 to 2. We're going to have 4 little sub-rectangle grids here. You can see I've drawn in 4 dots in the middle to represent the midpoints. Now, it's important for us to note that we don't have a function to substitute these points into. Like this first point right here, of course, would be 1/2, 1/2. But unlike our last example, we don't have a nice function where we can just plug that in. That's where the contour map is really coming into play. The contour map, as you look at these little contours here, like for example, if I were to say what's f of 1, 1, well at the point 1, 1, the height z would be 3. That's what these little lines are all about. So even though I can't plug a point in directly, we can get some estimates all the same. Let's also look at each subrectangle. For each subrectangle, you can see that the base is always going to be 1. The height's always going to be 1. That's your delta x and delta y. So that's kind of nice to always have an area of 1. Why do we bring this up? Well, we're trying to get this average value of the function going here. So we've got f average, and we can say 1 over that value of the area. So that's 1 over 4. And then inside we're going to always have the area of the base multiplied to the height. Now the area of each base is going to be a 1. So that's kind of nice. And I could say, hey, we're going to have to work out 4 of these rectangular prism volumes. But we're going to have a 1. You can say, well, what about the height? We're going to just have to do some estimating. And you can say right here is we're looking at this maybe about 1.3 or 1.4 as we're looking at this. By the way, sometimes even doing a problem for a second or a third time, you won't always come up with the same exact estimate. But you're trying to go between 1 and 2. So 1.4 or 1.3 wouldn't be a bad guess. Let's come up here. Again, we're going to have a base, area of the base is 1. In parentheses, we'll have our height, maybe about 3.2, perhaps, something like that, or 3.3. It's definitely, you could go either route. Let's come back down here. For this one in the bottom, maybe this is the easiest one. Maybe this would be a 3. And then finally, with an area of the base of 1, up here we might say that this could be perhaps a 5.2, 5.3, something like that. So as we're doing this, we understand that ultimately we're just getting an estimate right now. We're not getting something exact. So we're getting 1.4 plus 3.2 plus 3 plus 5.3. Work that all out, and you can see we're getting 12.9. If we took 1/4 of 12.9, you can see an estimate, no less. As we divide that by 4, we might get something such as 3.225. So In the next section, we're going to move beyond just estimating. In our book, we're going to be looking at page 1005, 1006, numbers 1, 3, 5, and 9.